introduction of spherical mirrors, now we know that concave and convex have a center curvature of which they are part of, as in the concave mirror and the convex mirror are part of a sphere, a hollow sphere, and that hollow sphere is having a center, and that also is the center of curvature for the concave or convex mirror. And that hollow sphere would also be having a radius of curvature, and that would also be the radius of curvature magnitude wise for the convex and concave mirror. Now, with this background, we have also studied that if my aperture is small, then all the parallel rays, when I say parallel to the principal axis, they intersect at the principal axis at one point, that is known as focus, or for the case of convex mirror, they appear to come out from one point, that is focus. So for a concave mirror, I have a real focus, and for a convex mirror, I have a virtual focus. Now, with this idea, we can understand how image formation is taking place and where would the image form if I know the location of the object. So let's understand the relation between object, image and focal length, or rather object distance, image distance and focal length. But in order to do this, we need to first make it clear, or rather define a sign convention. When I say sign convention, it's very similar to your XY system which we have read in the very initial chapters of physics. But this sign convention is slightly different. There's only a small twist to it. What you should remember about this sign convention is, I take all the measurements from pole. Remember pole, because all the measurements would be taken from pole. In the direction of light, all the measurements are positive. So positive means in the direction of light. DIR, and this means direction of light. When I say light, it's light rays. Similarly, it's needless to say that negative would be in the opposite direction. In the opposite direction of light. Any measurement done up the principal axis is positive, and any done below the principal axis is negative. Again, positive is up from principal axis, and to complete it, negative would be down from principal axis. So if we combine these 5 points, I can fully understand object distance, image distance, focal length and radius of curvature for a spherical mirror. When I say spherical, it is the combination or rather a club of convex and concave mirror both. Now, if we take a small diagram to understand the sign convention in a proper way, this is your concave mirror and this would be your convex mirror. Principal axis would be this thing. This is my pole. So any measurement which I would be doing to the right of it, which is in the direction of light, because light has to travel in this way, because this is the reflecting surface which I have. In this direction, a measurement will be positive. So from pole towards the right, it's positive, which means this half is positive from the pole towards the right. But this is the opposite in the left direction, so this is negative. So all the points which are to the left of your principal axis, or rather left of the pole in the principal axis, it's negative, and to the right it's positive. Similarly, if we take any measurements up, this is positive and down is negative. Again, in this situation also, light has to travel this way. So measurement from pole in this side, this is positive, negative, this again is your positive, and this is your negative. I know that the radius of curvature would be measured in the case of concave mirror in this side, because this is part of a sphere which is like this. I can complete this diagram to make a sphere, and center of curvature would be here. So radius of curvature would be to the left side. So in this case, R, which denotes radius of curvature, is negative. Similarly, focal length would also be in this side. So F would be negative. Come to here. Here, this is part of this sphere. So center would be here. So radius of curvature measurement would be to the right, which means in the case of convex mirror, my R would be positive. What about focal length? Again, focus would also be on this side. I've seen that in the case of earlier diagrams, the virtual focus thing. So this is also positive. So now we have a complete understanding of radius of curvature and focal length for the concave and convex mirror, and the sign also. There's something called U and V. Object distance, or the distance of object away from pole, is denoted as U, and distance of image away from pole is denoted as V. So you can write here object distance, and this is your image distance. Now, with this background, let's understand the relation between U, V, R and F. We'll first take the case of concave mirror, and we will follow all the sign conventions. Let's say this is your concave mirror, and this is having a very small aperture. When I say very small aperture, this arc kind of behaves like a straight line, because for a small aperture, what happens is your circular arc would behave like a straight line, or rather this is a kind of a curved surface. It would behave like a plane, right? This is your pole. This is your principal axis. This is the principal axis meets the mirror is your pole. Now, this is your C, center of curvature, and around midway you will have something known as focus. Let's say I've kept an object here, point size object, O denotes object. Ray of light which travels along this path. For it, this is my normal. This angle over here is your I. Just write an I over here. This angle is I. I'm taking this arrow to denote the angle measurement here. The same angle would be formed by the reflected ray too. This is my incident ray, and this is my reflected ray. And both of them would subtend the same angle with the normal. So even this is your I. Now, over here, let's say this is your alpha. This is your beta, This is your gamma. And let this point be some x. As I have taken this as a very small aperture, this XP curve thing is going to behave as a straight line. Now I can make 3 triangles from this diagram. First, the OXP. This is your O. This is X. This is P. This angle is your alpha. Similarly, I can also make this triangle XC. Let this thing be I. I denotes image. So let's draw XCI. This is your X, this is your C, this is your I, this is your beta. And this angle is equal to I. And this angle is gamma. So in this situation, beta plus I has to be gamma, property of triangle. So beta plus I would be gamma. And if you come to think of it, I can also draw another triangle similar to this and this, just containing X, C and O. This is X, this is O, this is C. This angle is your beta, this angle is your alpha, and this angle OXB. Let's see what this angle is. OXC. This is your I. So alpha plus I gives you beta. This is equation number 1 and this is equation number 2. If you subtract these two equations, my I would get cancelled away. What I will have is beta minus alpha is equal to gamma minus beta. Take this beta on the left side and alpha on the right side. What you'll get is twice of beta is equal to alpha plus gamma. Twice of beta is alpha plus gamma. Now I know that these angles alpha, beta, gamma are all small angles. Why? Because I have taken the aperture to be very small. And there's one more term which comes along with the small aperture thing, that is paraxial rays. When I say paraxial rays, what I mean is the rays are almost parallel to the principal axis, which means they would make very small angles to principal axis. So alpha, beta, gamma all are making very small angles. If alpha, beta, gamma are very small because of the small aperture and paraxial rays, I can approximate alpha, beta, gamma as tan beta, tan alpha and tan gamma. So in place of 2 beta is equal to alpha plus gamma, I know that alpha can be approximated as tan alpha, beta can be approximated as tan beta, and gamma can be approximated as tan gamma, which means in place of beta I can write 2 tan beta is equal to tan alpha plus tan gamma. I also know that in this triangle tan alpha is equal to xp by po. Similarly, I can draw a triangle XIP. In that, I will have tan gamma as XP by PI. And I can also draw XCP. In that, tan beta would be equal to XP by PC. So let's substitute these three ratios into this equation. What I would get is twice of XP upon PC is equal to tan alpha, which is XP upon PO plus tan gamma, which is XP upon PI. In this thing, XP is common. I can cancel them out. So what I'm left with right now is 2 upon PC is equal to 1 by PO plus 1 by PI. Now this is a groundbreaking result. Why? Because now I have the relation between PC, which is denoting the radius of curvature magnitude, PO denoting the separation of object from pole, PI denoting the separation of image from pole. But these are separation or magnitude values. Now, I don't have the liberty or freedom of having the magnitude values always with me. Because this U, object distance, V, image distance, or R, the center of curvature, is always given with sign convention. And for a concave mirror, as we have taken in this situation, R is negative, U is also negative. I don't know about V, but this diagram says V would also be negative. So U, V, R all are negative, but PC, PO, PI are positive. Write this thing down. PC, PO and PI are positive, but U, V and R are negative. So to substitute U in place of PO, V in place of PI and R in place of PC, I need to adjust their signs by using sign convention thing. So what I will have is 2 by PC, which is minus of R, because R is negative. So negative and negative is positive. This is equal to 1 by PO. PO is again positive, but U is negative, so this is minus U. Plus 1 by PI, again PI is positive, but V is negative, so minus V. Minus minus gets cancelled all of the way. So what you have is 1 by U plus 1 by V is equal to 2 by R. And I also know that F, focal length, is equal to R by 2. This we have calculated much before. I can substitute this value because if F is R by 2, 2 by R is 1 by F. So you can write this thing over here also. And this becomes your mirror formula. This is your so this tells you the relation between object distance, image distance, radius of curvature and focal length. This we have done for concave mirror. But if we draw a similar diagram, ray diagram, these diagrams are known as ray diagram. So if we draw a similar ray diagram for convex mirror, ray diagram for convex mirror, would also yield the same result. would also yield the same thing or the same formula. And this is my that formula. 1 by u plus 1 by v is equal to 2 by r is equal to 1 by f.